This galaxy should not exist. She was born when the universe was less than 300 million years old. It's small, it's dense, and it's full of nitrogen, an element that should only appear billions of years later. James Webb found her, and with it, a question that can change everything. What if our entire universe is the inside of a black hole? On December 25th, 2021, an Ariane 5 rocket lifted off from French Guiana with a cargo so precious that the scientific world held its breath. On board was a James Webb Space Telescope, or James Webb, a $10 billion machine designed to peer back into the beginning of time. It wasn't just another telescope, it was a time machine. And 3 years later, it's doing just that, showing us a universe no one predicted. Before James Webb, our view of the early cosmos was limited. Hubble, a hero of astronomy for decades, revealed distant galaxies like GNZ 11, seen when the universe was about 400 million years old. It was a monumental feat, but Hubble had limits. Its 2.4-meter mirror and its sensitivity primarily to visible and ultraviolet light prevented it from seeing beyond a certain cosmic veil. The light from older galaxies, stretched by the ever-expanding expanse of space, reaches us as infrared, nearly invisible. And that's where James Webb came in. With a 6.5-meter golden mirror composed of 18 hexagonal segments and instruments tuned to capture infrared light with pinpoint accuracy, the James Webb was designed to see precisely this kind of light, the light that has traveled more than 13 billion light years to reach us. And when it began its observations, scientists expected to confirm theories. What they didn't expect was for the universe to start lying to them. Because, according to current cosmological models, based on the Lambda CDM model, the early universe should have been a chaotic, rarefied place, dominated by primordial gas and simple, primitive stars called Population 3. Galaxies at this stage should have been small, faint, and slow in their evolution. But what the James Webb found was the opposite. Bright, massive galaxies, rich in heavy elements, emerging when the cosmos was still learning to exist. The first big surprise came with galaxies like JWST Z14-0, with a redshift of 14.32, meaning we're seeing the light that came from it when the universe was only 280 million years old. Then came MOMZ14, with a redshift of 14.44, even more distant. But what's truly shocking isn't just their distance. It's what these galaxies are. They're not disorganized clouds of gas. They're dense structures, forming stars at breathtaking rates, with chemical compositions that indicate multiple stellar generations had lived and died before them. This shouldn't be possible. Not at this stage of the universe. Not with the laws we know. And most intriguingly, they're appearing in far greater numbers than models predicted. What was once considered a rare anomaly now appears to be a common, and even dominant, phase of cosmic evolution. The universe isn't forming slowly. It's exploding in complexity from its earliest stages. James Webb isn't just expanding our field of view. He is defying cosmic chronology. It is forcing us to ask, was the Big Bang really the beginning? Or was there something before? What if the history of the cosmos is longer, denser, more mysterious than any current theory can contain? This is the new universe. Not the universe we imagine, but the universe that really exists, and we are just beginning to see it. Imagine looking up at the sky and seeing a point of light so distant that its existence defies the logic of time. That point is MOMZ14, one of the oldest galaxies ever detected by humanity. Its light traveled more than 13.4 billion light years before reaching the James Webb sensors. This means we're seeing MOMZ14 as it was when the universe was only about 280 million years old, less than 2% of its current age. It's as if we're watching the second chapter of the story of everything, and it's already full of twists and turns. But what makes MOMZ14 so extraordinary isn't just its age. It's everything it shouldn't be. According to traditional cosmological models, galaxies in this period should be small, faint, and composed almost exclusively of hydrogen and helium, the primordial elements. They should be just beginning to form their first stars at a slow pace in a still chaotic universe. MOMZ14, however, ignores all these rules. It's tiny, only about 500 light years across, nearly 200 times smaller than the Milky Way. But despite its size, it's incredibly bright. So bright that it defies models' ability to explain how so much energy could be generated so quickly. And this brightness stems from a secret. MOMZ14 is in a state of frenetic star formation. Stars are being born within it at a rate that, in cosmic terms, is almost violent. It's as if the entire universe is screaming, "We're here! Now!" The most intriguing thing? There's no sign of a supermassive black hole at the center. In massive galaxies in the present-day universe, these gravitational monsters are essential. They regulate star formation, limit galactic growth, and shape the system's structure. But in MOMZ14, nothing. No radiation jet, no accretion disk, no spectral signature of a massive central object, like a bustling city with no mayor, no laws, no control, and yet functioning perfectly. But the real shock came with the spectroscopic analysis performed by James Webb. When scientists examined the galaxy's light in detail, they found something that simply shouldn't be there: nitrogen in extreme abundance. And not only that, the type of nitrogen found as a result of advanced stellar processes is produced in massive stars that live, burn their fuel rapidly, and explode as supernovae. The nitrogen is then recycled into new generations of stars. In other words, before MOMZ14 even existed, other stars had already been born, lived, and died. This implies a timeline that does not fit the standard model. Would the universe have had enough time to form stars, watch them evolve, explode, enrich the interstellar medium with heavy elements, and only then form galaxies like MOMZ14 in less than 300 million years? It's like finding a 50-story building in a city that, according to records, was still being planned. Something is out of place. Or, more likely, our chronology is wrong. MOMZ14 is not just a galaxy. It is a message from the deep past, written in light and chemistry. And she says clearly, you have underestimated how fast the cosmos can evolve. They underestimated how early complexity can arise. And they underestimated how ancient what they call the beginning might be. She is a beacon in the twilight of time, a warning, and perhaps the first sign that the history of the universe is much richer and much older than anyone dared to imagine. When the James Webb began scanning the far reaches of the early universe, scientists expected to find rare, faint galaxies, perhaps a few anomalies. What no one anticipated was an entire population of strange, bright, and precocious galaxies emerging as red dots against the otherwise dark background of the cosmos. Today, these galaxies have a name: little red dots. But what seemed like an isolated curiosity is turning into a quiet revolution in cosmology. MOMZ14 is not a unique case. It's just the most famous of a legion of ancient galaxies that James Webb has revealed in campaigns like JWST, Source, and Cosmos Webb. They appear in all directions, at times close to the dawn of time, between 200 and 400 million years after the Big Bang. They are small, yes. Many are less than 1,000 light years across, but they are disproportionately luminous, especially in the infrared, indicating intense star formation. And most surprisingly, they are chemically rich, with levels of heavy elements like oxygen, carbon, and nitrogen that should only exist much later in cosmic history. This is not just intriguing. It is deeply problematic for current science, because, according to the Lambda CDM model, the dominant theory of universe evolution, galaxies like this shouldn't exist at this stage. The early universe was supposedly a simple place: clouds of primordial gas, hydrogen and helium, slowly collapsing under gravity, forming the first stars, the mythical population 3 stars, which would take hundreds of millions of years to enrich the interstellar medium with metals. Only then, much later, would galaxies with structure, brightness, and complexity emerge. But the little red dots ignore this script. They are there, shining, forming stars, enriched with heavy elements, and in numbers far greater than any simulation predicted. Some scientists are already talking about a crisis in cosmology, not because the theories are wrong, but because the data are telling us that the universe was far more efficient, far faster, and far more organized in its earliest moments than any model could predict. It's as if the cosmos skipped steps, or as if we underestimated the speed at which gravity, radiation, and cosmic chemistry could act on a universal scale. And there is another, even more disturbing possibility. Maybe we are not seeing the first galaxies, but rather the second or third generations. In other words, even before MOMZ14 or the Little Red Dot existed, there was already an entire cycle of stellar formation and death, a hidden universe, invisible until now, that prepared the ground for this explosion complexity. Some researchers suggest that these galaxies may be dense cores of stars, the embryos of the larger galaxies that would come later. Others believe they represent a universal phase of galactic evolution that Hubble could never see, not for lack of technology, but because the light from these galaxies is so redshifted that only James Webb can capture it clearly. But the most fascinating thing is the pattern. They are appearing in excess, so many that the models need to be adjusted or replaced. If the early universe was full of these red dots, then the history of galaxy formation needs to be rewritten. And if they are so common, perhaps we, in our large, slow-moving, mature galaxy, are the anomaly. The little red dots are not just distant objects. They are eyewitnesses to a universe that was born running. And as we continue to meet them, one question grows in volume. Was the Big Bang really the beginning? Or just the echo of something even older? For decades, modern cosmology has rested on a solid pillar, the lambda CDM model, an elegant, mathematically robust theory. It describes a rapidly expanding universe dominated by dark energy, lambda, and cold dark matter, CDM. This model has successfully explained the cosmic microwave background, the formation of large structures, the distribution of galaxies, and even the acceleration of the universe's expansion. It has been crowned the standard model of cosmology. But now, he is being put to the test, and perhaps, for the first time, failing. Because the lambda CDM model predicts a universe that starts out simple and slowly becomes structured. First, small fluctuations in the density of primordial gas. Then, clumps of dark matter that attract hydrogen. Then the first stars, cool, massive, short, that burn fast and explode. Only much later, billions of years later, do these stars group together into small galaxies, which collide, merge, and grow until they form giants like the Milky Way. It is a gradual, hierarchical, predictable process. But what James Webb is showing is not gradual. It's explosive. Galaxies like MOMZ14 and the little red dots are not early stages of formation. They are mature, dense, chemically evolved structures arising in a universe that, according to model, was still learning to exist. And they are not rare. They're showing up in numbers that simply don't fit the simulations. When scientists compared the James Webb data with the lambda CDM predictions, the results were alarming. There are 5 to 10 times more massive galaxies in the early universe than the model allows. It's as if, when you look at a newly planted forest, you find centuries-old oak trees everywhere. Something is wrong. Or the forest grew 1,000 times faster than expected. Or the seeds were already there before planting. This discrepancy is not a small adjustment. It is a structural crisis. If the universe managed to form such complex galaxies so early, then either gravity acted with unexpected efficiency, or dark matter behaved differently, or the expansion of the universe itself was slower in the early moments, allowing structures to form more quickly. Or, in an even more radical scenario, fundamental physics may be different at the beginning of time. Some researchers are already proposing modifications to the lambda CDM model: hot or self-interacting dark matter, time-varying dark energy, cosmic inflation with different phases. Others go further. What if the Big Bang was not the absolute beginning, but rather an event on a much longer timeline? What if the universe went through cycles of contraction and expansion, or did arise from a collapse in the parent universe, as the Big Bounce theory predicts? Most shockingly, no proposed modification so far can fully explain the James Webb data. The little red dots remain an enigma, and each new observation seems to increase the pressure on the prevailing theory. This does not mean that lambda CDM will be discarded. Scientific models rarely die all at once, but they evolve. And what we are experiencing could be the beginning of a new era in cosmology, a revolution comparable to that which occurred with relativity or quantum mechanics. Because the universe isn't just showing new galaxies. He is showing that our cosmic story may be incomplete or even wrong. And if that's true, then James Webb isn't just a telescope. It's a detonator. And the explosion is just beginning. In every massive galaxy we know, there's a secret at its heart, an invisible monster, a gravitational abyss from which nothing escapes, not even light. The supermassive black hole. In the Milky Way, it has 4 million times the mass of the Sun. In giant elliptical galaxies, it reaches billions. And it's not just a cosmic accident. It is a central piece of the galactic mechanism, regulates star formation, controls the growth of the galaxy, releases jets of energy that can heat or cool interstellar gas. He is, in many ways, the silent architect of galactic evolution. But then we come to MOMZ14, a galaxy in full stellar activity, dense, rich in heavy elements, born the first 300 million years of the universe. And there is no sign of a black hole at the center. None. Nothing in the James Webb observations indicates the presence of an active nucleus. No characteristic brightness of the accretion disk. No X-ray or radio emissions. No gravitational distortion on nearby stars. It's like finding a bustling city with factories humming, streets bustling, and energy flowing, but no power plant, no power grid, no central control center. How is everything working? And who is in charge? This absence is not just curious, it's revolutionary. Because for decades, scientists believe that black holes and galaxies evolve together in a cosmic feedback loop. The more the galaxy grows, the more matter feeds the black hole. The more a black hole consumes, the more energy it releases, slowing down or accelerating the formation of new stars. It's a delicate balance, tested in hundreds of galaxies in the nearby universe. But in MOMZ14, that balance simply doesn't exist. Did black holes come later? That early galaxies formed without a central engine. And only later, over time, did these monsters emerge? Or are they there, but in a form we haven't yet detected? Perhaps they are primordial black holes, formed not from the collapse of stars, but directly from the collapse of extreme densities in the early universe. Invisible, silent, still dormant. Another, even more radical possibility. Perhaps black holes are not necessary for small, dense galaxies in a denser universe. With cooler gas and more efficient gravity, perhaps star formation could occur in an uncontrolled manner, without the need for regulators. It's as if, in the early days of the cosmos, galaxies were wild, without laws, without control, just being born and burning energy at a dizzying rate. But this raises an even bigger question. If galaxies like MOMZ14 can exist without black holes, could the relationship between black holes and galaxies be the opposite of what we think? Instead of the black hole controlling the galaxy, does the galaxy, in its early stages, create the black hole? Not as an engine, but as a byproduct, a gravitational residue of so much concentrated stellar chaos? And if so, then the early universe was not a place of slow order, but of local explosions of density, where stars were born, died, and collided so quickly that, before long, the gravitational collapse itself generated a black hole. Not at the beginning, but at the end of a violent cycle. The absence of the black hole in MOMZ14 may be the strongest evidence, yet that galactic evolution has phases we do not yet understand. Phases where physics is extreme, gravity is dominant, and the rules that apply today simply didn't apply yesterday. And maybe, just maybe, we're seeing the universe before the monsters arrived, before the birth of kings, when the cosmos was still a lawless land, and the galaxies, small and red, were the first flames in the dark. There is an element in the universe that carries a silent secret, nitrogen. It is not the most abundant, it's not the heaviest, but it is one of the most revealing, because nitrogen was not born in the Big Bang. He was not part of the primordial broth of hydrogen and helium that gave rise to the cosmos. Nitrogen is a product of stellar evolution. It is made inside massive stars in complex nuclear reactions and released only when those stars die, in supernova explosions or intense stellar winds. It is, in essence, the ash of the first generations of stars. So when James Webb detected extremely high levels of nitrogen in galaxies like MOMZ14, which existed when the universe was less than 300 million years old, scientists felt the ground drop away, because that shouldn't be possible. There simply wasn't time. To produce nitrogen in significant quantities, it is necessary to massive stars being born, live for millions of years, not much in cosmic terms, but not insignificant, die in supernovas, enrich the surrounding gas. This gas forms new stars, which also produce more nitrogen. It is a cycle that in traditional models takes hundreds of millions of years to establish itself. But in MOMZ14, this cycle was already underway, even before the universe was 300 million years old. It's like finding a book written in a sophisticated language in a civilization that, according to records, was still learning to draw symbols. Something is out of sync, or time passed faster, or the beginning was much earlier than we think. The presence of nitrogen is not just a chemical fact. It's a cosmic age mark. And she is saying, clearly, there was stellar life before MOMZ14. Stars were born. They lived. They exploded. And they left behind an enriched universe, a fertile ground for galaxies like this to flourish very soon. But how? How did the universe have time to complete this cycle so quickly? One possibility is that the first stars lived and died much faster than we predict. Population 3 stars, the first in the cosmos, were massive, hot, and unstable. Some may have lived only a few million years before exploding. If the early universe was denser, with gas collapsing faster, perhaps millions of stars were born in successive waves, enriching the interstellar medium in record time. Another, even more radical theory. Perhaps the universe already had heavy elements before the Big Bang, in models of cyclic universes or brane collision theories in the multiverse. Material from a previous universe may have survived the collapse or transition. In other words, the nitrogen in MOMZ14 was not made after the beginning, but it came from before. And there is an additional clue. The ratio of nitrogen to other elements in MOMZ14 matches what we see in very old star clusters in the Milky Way, such as globular clusters. This suggests that the formation environment was extremely dense, with stars being born in tight clusters, almost like cosmic beehives. A scenario where star formation is so efficient that, within a few million years, the gas is already enriched. Nitrogen, then, is not just an element. He is an eyewitness. He is telling us that the early universe was not a chemical wasteland. It was a high-speed stellar nursery, a place where stars were born, died, and recycled matter with an efficiency that defies imagination. And if that's true, then the Big Bang wasn't the beginning of chemistry. It was just the beginning of what we got to see. And the true dawn of time may be hidden in nitrogen atoms, traveling for 13 billion years to tell us a story we still can't decipher. Imagine a perfectly random universe. Galaxies scattered haphazardly, spinning in all directions, like leaves in the wind in a directionless storm. This is how standard cosmology describes a large-scale cosmos, isotropic, homogeneous, with no privileged direction. The cosmological principle, one of the cornerstones of modern physics, says that on sufficiently large scales, the universe looks the same in all directions. There is no center. There is no up or down. There is no left or right, just ordered chaos. But what if this principle is wrong? In recent years, increasingly precise observations have revealed something disturbing. Spiral galaxies do not appear to rotate randomly. Contrary to what one would expect, there is an excess of galaxies rotating in a specific direction, as if the entire cosmos had a slight preferential spin. Studies that analyze thousands of galaxies, crossing data from the Sloan Digital Sky Survey, Hubble, and now James Webb, found statistical patterns that cannot be ignored. In certain regions of the sky, there are up to 10% more galaxies rotating counterclockwise and clockwise, and this pattern repeats itself on a large scale. This shouldn't happen. In a truly random universe, the split should be 50-50. The observed imbalance is small but significant, and most importantly, it cannot be explained by measurement error or instrumental bias. The analysis was done blindly, with algorithms automatically identifying the direction of the spiral strokes. The result persists. Some scientists call this cosmic anisotropy, the idea that the universe has a preferred direction, a hidden axis, as if aligned by a primordial force or condition. And if this is true, then the cosmological principle, the foundation of all general relativity and modern cosmology, may be failing on gigantic scales. But why would that happen? One possibility is that the primordial density field itself in the early universe was not perfectly uniform. Small fluctuations amplified by cosmic inflation could have created a collective flow of rotation, like eddies in a river that originates with a side current. Another theory suggests that the universe may have absorbed an angular torque during the Big Bang, as if it were born spinning. But a fully rotating universe violates the fundamental symmetries of general relativity, unless there is something outside of it exerting influence. And this is where things get really weird. Some researchers propose that this galactic alignment may be a fingerprint of a larger universe, a parent universe in which ours is embedded. If our cosmos arose inside a black hole in another universe, for example, the rotation of that black hole could have been transferred to our expanding universe. It would be like a top spinning inside another top. The movement of the whole affects the part. There are even those who see this as a possible explanation for the matter-antimatter asymmetry, why there is more matter than antimatter in the universe. Perhaps the cosmic spin favored one type of particle over another at the birth of the cosmos. But perhaps the deeper implication is philosophical. The universe is not random. It has a direction, one sense, a story written in spiral arm curves, in movements that repeat themselves as an almost conscious pattern. And if the galaxies are aligned, how many other patterns are we blind to see? Because after all, the universe may not be a coincidence. It could be a system, an organism, or maybe a cosmos that revolves within something much larger than we can imagine. There's a limit beyond which nothing can escape. No light, no sign, no information. It's the event horizon of a black hole, the final frontier. Outside, the universe continues. Inside, what happens is one of the greatest mysteries in physics. But what if we tell you that we are already on the inside? May every galaxy we see, every star that shines, every atom in our body, is everything part of the interior of a gigantic black hole? That the entire universe, with 13.8 billion light-year radius, is not the outer cosmos, but rather the inner space of a gravitational collapse in another universe? This idea is not science fiction. It is a serious hypothesis, known as Schwarzschild cosmology, or the black hole model of the universe. And it is gaining momentum in the face of the James Webb discoveries, cosmic anisotropy, and the enigma of early galaxies. The logic is surprisingly elegant. When a massive star collapses, a black hole forms. At the center, general relativity predicts a singularity, a point of infinite density. But what happens inside? Nobody knows. The laws of physics break. But what if, instead of an end, this collapse is a beginning? Some physicists, like Nikodym Poplawski and Einstein before him, noticed something intriguing. The mathematical solution for the interior of a black hole, described by the Schwarzschild metric, can be extended to describe an expanding universe on the other side of the event horizon. In other words, what for an external observer is a gravitational collapse, to an internal observer it may look like a Big Bang. In this scenario, the Big Bang was not an explosion in empty space. It was a moment when the matter of a parent universe collapsed into a black hole and gave birth to a new bubble of space-time. Our universe is an idea that rewrites everything. Time did not begin out of nothing. It started inside something. Space does not expand into a void. It expands because it is the interior of an extreme gravitational structure. And there's more. Every black hole in our universe could be generating a new universe inside it, a baby cosmos, with its own laws, its own galaxies, perhaps even its own life forms. It would be a process of infinite cosmic reproduction, a multiverse not of parallel bubbles, but of nested universes, like Russian dolls of gravity and time. This theory may also explain one of the greatest enigmas in physics. Why do the fundamental constants of the universe seem so perfectly tuned to allow life? If daughter, Universes inherit slightly altered properties from the conditions of the black hole that spawned them. Then only the most stable ones would survive and be more likely to spawn black holes, perpetuating the cycle. It's cosmic natural selection. Universes that favor life also favor gravitational reproduction. And there are indirect clues. The entropy of a black hole, a measure of its internal information, is colossal. And interestingly, the total entropy of the observable universe is comparable to that of a black hole of the same size. Coincidence? Or evidence that we are, in fact, inside one? If this is true, then James Webb is not looking into the past of the universe. You're looking at the walls of our bubble universe. And every distant galaxy may be an echo of the gravity that created us. It's not the end of physics. It's the beginning of a new vision. One where the cosmos is not an accident, but a living system, self-replicating, and maybe eternal. The Big Bang is a story we all know. A point of infinite density, an instant zero, an explosion that gave rise to time, space, matter. But what if this story is incomplete? What if the Big Bang wasn't the beginning of everything, but just the beginning of what we can see? There's a theory that challenges the idea of the singularity, the Big Bounce. According to this hypothesis, the universe did not arise from nothing. He was reborn after a cycle of contraction, perhaps from a previous universe. Gravitational collapse reached a limit, and then, instead of forming a singularity, it rebounded like a crushed ball that, upon reaching its limit, explodes outwards. And this jump was what we call the Big Bang. But what could cause this rebound? In Einstein's general relativity, when matter collapses, nothing can prevent the formation of a singularity. But Einstein did not work alone. In collaboration with mathematician Einstein-Cartan, he developed an extension of relativity that includes a fundamental property of matter, the spin of particles. This theory, known as Einstein-Cartan relativity, introduces a new concept, space-time torsion. While the curvature of space-time describes gravity, torsion describes how space can be twisted by the intrinsic rotation of particles. As if the very fabric of the universe had a granular structure capable of withstanding extreme compression. At normal densities, torsion is negligible, but at quantum scales close to total collapse, it becomes dominant. And here's the crux. Torsion generates a repulsive force. The higher the density, the harder it pushes out. So when a universe or a star collapses, there's a limit beyond which gravity cannot prevail. The twist says, enough, and collapse becomes expansion. There is no singularity. There is no infinity. There is a rebound. This model offers an elegant solution to one of the biggest problems in physics, the singularity. A point of infinite density is not only impossible to measure, it is a sign that the theory has failed. The Big Bounce, on the other hand, keeps the laws of physics intact. Time does not start from nothing, continues. The universe is not born from scratch. He transforms. And there's more. This jump could explain the accelerated expansion of the universe without needing dark energy. The echo of the rebound would still be acting. It could also explain the homogeneity of the cosmos, because the pre-collapse universe was already in equilibrium. But the most fascinating thing is the cyclical implication. If the universe can collapse and be reborn, perhaps we are in an endless cycle of cosmic deaths and rebirths. Every Big Bang followed by a big crunch, and then another big bounce. An eternal pulse of the cosmos. And if that's true, then the galaxies James Webb is seeing, MOMZ14, the little red dots, the nitrogen at the dawn of time, are not the first objects in the universe. They are the first survivors. Fragments of a previous cycle. Stars that lived, died, and left their legacy in atoms that survived the jump. The Big Bounce turns time from a straight line into a circle. The universe ceases to be a story with a beginning, middle, and end, and becomes an eternal return. Not an accident, but a rhythm. And maybe, just maybe, the universe is not expanding by chance. Be breathing. James Webb showed us galaxies that shouldn't exist. It revealed chemistry to us where there should only be gas. It made us wonder if we live inside a black hole, if time has skipped before, if the universe has a hidden axis. But perhaps his greatest discovery isn't a galaxy, an element, or theory, be the end of cosmic certainty. For decades, science believed it had a good map of the universe. The lambda CDM model, cosmic inflation, general relativity, it all seemed to fit together. But James Webb didn't come confirm, came to destabilize, to show that the early universe is denser, faster, more complex than any simulation predicted. And now, faced with this avalanche of data, scientists aren't closing the books. They're opening new ones. And the most exciting thing is that James Webb is just the beginning. In a few years, a new giant will enter the scene, the Nancy Grace Roman Space Telescope. While James Webb is a precision observatory capable of focusing on small windows of sky in extreme detail, Roman is designed to scan vast areas of the deep universe with the same resolution as Hubble, but in a field of view 100 times larger. It will be like exchanging a flashlight for a spotlight. When Roman begins its observations, it will not only confirm the galaxies that James Webb found, he will multiply them. You can discover hundreds, thousands of little red dots, mapping their distribution, their rotations, their chemistries. And in this map, perhaps we will find patterns, clusters that suggest a cosmic axis, alignments that confirm anisotropy, or even structures so large that they challenge the notion that the universe is homogeneous. Together, James Webb and Roman will form a new perspective on the cosmos, one that combines depth and breadth. They're not just seeing far, they are seeing at the right time. Because now we know, the first 500 million years of the universe were not a prelude. They were an entire act, perhaps the most important. But the revolution doesn't stop there. Future telescopes, like the Vera C. Rubin Observatory, will map the entire night sky every few days, detecting changes in real time. ESA's Laser Interferometer Space Antenna, LISA, will listen for gravitational waves from merging supermassive black holes, perhaps even the echoes of collisions from the early universe. Each of these instruments is a new door, and they're all opening at the same time. And we, here on Earth, are the first conscious beings to witness this moment. We are not just spectators. We are interpreters of the cosmos. Every James Webb discovery is a letter from the deep past, written in light and chemistry, and we are the only ones capable of reading it. We may never have all the answers. Perhaps the universe is infinitely stranger than any theory. But the fact that we are here, looking back in time, asking, where do we come from? Why do we exist? This in itself is a cosmic miracle, because the universe doesn't just expand. He thinks through us. And as long as we continue to look at the stars, we will not just be discovering the universe. We will be helping him get to know himself.